This is the next video for differentiation, and we're going to look at how we differentiate trig functions. So in this video we're going to look at how we differentiate sine and cosine, and some of the other trig functions. So as you can see on the screen, you can see we're going to start with sine, and you can see a sine wave, and that sine wave is measured in the angles are measured in radians. So if we just have a quick look at this sine wave, you can see, that if I superimpose on top of it the gradient graph, so at this point here, when x is pi over 2, you can see the gradient will be 0, so I'm going to put at 0. At this point here, where x is 3 pi over 2, the gradient also will be 0. Now, when x is 0, if you put a tangent line on, that tangent line will be 1. So I'm going to put a point at 1. Now, that is only true if your sine wave is drawn in radians. Here at pi, the gradient is -1. And here again at 2 pi, the gradient will be 1. So if I draw the graph on top, you will see that what you get is a cosine wave. That means that if y equals sine x, then dy dx is cos x. But just being able to draw the graph is not enough to prove that that is true. So we're going to look at the proof. So this is a proof that you must learn. Now, it was on the exam in 2023, so one of the other ones might come up, but it's a good idea to learn the process. So you can see what we've been given. We've been given that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. Now, those come from our small angle approximations. Now, if you remember, when you did small angle approximations, they only work in radians. So if you remember, in your work on small angle approximations, sine x can be replaced by x if x is small and measured in radians. So therefore, sine h can be replaced by h. So therefore, sine h over h is approximately h over h, which is 1, which leads to 1. And that is where this statement comes from. If you use small angle approximations for cos, that will lead you to this statement. So we're going to use first principles. Now, if you remember in the first principles formula, it's in the formula book. I'm going to write it down in a minute. We need two things. We need f of x, or our function that we are differentiating is sine x. We also need f of x plus h. So that's sine of x plus h. Now, we're going to use, if you remember, the addition rule for sine to expand that. So we get sine of x cos of h plus cos of x sine of h. Right, so I've got all the things that I need from a formula. So I'm going to write the formula down. So the formula from the formula book says f dash of x equals the limit as h tends to 0 of, and it's f of x plus h minus f of x over h. So I'm going to put in what I know. So it's the limit h tends to 0 of, so it's sine x cos h plus cos x sine h minus sine x over, over h. Now, in order to be able to replace some of this with those assumptions I was given, I just need to change the position of these two terms. So I'm going to do that. So I'm going to get the limit as h tends to 0 of sine x cos h minus sine x plus cos x sine h. I'm just going to share out h. Right, so notice the first two terms in the brackets. I'm now going to factorise out the sign. So I get the limit as h tends to 0 of sine x multiplied by cos h minus 1 over h plus sine cos x, sorry. And I'm going to put this in a bracket so it stands out, sine h over h. Now, remember what the assumptions said. Okay, and I'll just try and make it clear. Right, so cos h minus 1 over h tends to 0 as h tends to 0. So therefore, any term multiplied by that will also tend to 0. So you can write as h tends to 0, cos h minus 1 over h tends to 0. Therefore, sine x multiplied by cos h minus 1 over h also tends to 0. And as h tends to 0, cos x, sorry, my apologies, as h tends to 0, sine x, sine h over h tends to 1, therefore cos x sine h over h will tend to cos x. So therefore, f dash of x equals cos x. And that's your proof. And that's really important. So that's what you're trying to do. You're trying to embed the two things that you were given. Okay. Now, you can also do the same with cos x. Now, if you do a gradient graph for cos x, where the graph is drawn in radians, this is the graph you get. Okay. And you'll notice that that is negative sine x. Okay. Now, if you were going to do the proof, and this one might be one that you try on your own, it is exactly the same, apart from you start with f of x equals cos x, so f of x plus h would equal cos of x plus h. And again, you're going to use the addition rule for cos, so you'll get cos x cos h minus sine x sine h. But again, you'll get the same thing, and when you use those assumptions, you'll end up with cos x differentiating to negative sine x. Okay, so now let's have a little look. So what we've now got, we know that sine x differentiates to cos x differentiates to negative sine x, and negative sine x will differentiate to negative cos x. And it's really quite useful if you learn that little pattern. So we can now derive the formula for when you differentiate tan x. Now, it is in the formula book. Okay, so if y equals tan x, we know that y is sine x over cos x. Okay, so we can use the quotient rule. So remember, you use the quotient rule, u is sine x, v is cos x, u dash is cos x, and v dashed, if you differentiate cos x, you get negative sine x. Okay, and if we're doing the quotient rule, we also need v squared, which is cos squared x. Okay, so if we use the quotient rule, remember the quotient rule is vu dashed minus uv dashed over v squared. Remember, it's in the formula book in function form, so you can't get it wrong. So we get dy dx equals, well, vu dashed is cos squared x, and it's minus, and then uv dashed is minus sine squared x over cos squared x, which is v squared. So on the top, got cos squared x plus sine squared x over cos squared x. Okay, so that's 1 over cos squared x, which equals sec squared x. So if y is tan x, then dy dx is sec squared x. Now we could use the same approach to find the derivative of sec x, cosec x, and cot x. So we're just going to have a quick look at those. Okay, all right, so these are in the formula book. So sec x becomes sec x tan x. Cosec x becomes negative cosec x cot x. And cot x becomes negative cosec squared x. And you could be asked to show that in the exam. Instead of quoting the formula book, you could be asked to show that. So we'll just have a little look at a couple of them. Right, so I'm going to start with this one, y equals sec x. Now, remember what sec x is. It's 1 over cos x. Now, it's up to you. You could use the quotient rule, or you could use a bit of Dode. Now, for this one, I'm going to use Dode or the chain rule. So I'm going to write it as y equals cos x all to the power negative 1. Okay, so I'm going to differentiate it. So you differentiate around, so it's negative cos x to the minus 2, to negative 2. And then differentiate inside, so differentiate cos, that will give you minus sine x. So that's multiplied by minus sine x. So this will be y dx equals, it's going to be sine x, so negative times negative, positive over cos x all squared. Okay, now if you split that up, this is 1 over cos x multiplied by sine x over cos x, which is, so therefore dy dx is sec x tan x. Now again, you could do the cosec one exactly the same. I'm going to leave that for you to do. Just going to have a look at the cot one. Now again, there's a couple of different ways of doing the cot one. I'm going to do it. So I'm going to write cot, and I'm going to write it as cos x over sine x. And I'm going to use the quotient rule. Okay, so underneath I'm just going to write the bits. So, okay, so u is cos x, v is sine x, u dashed. Well, cos goes to negative sine x. V dashed will be cos x. Okay, and v squared will be sine squared x. And I'm going to use the quotient rule. So dy dx, so it's vu dashed. Okay, so that's minus sine squared x minus uv dashed, which is minus cos squared x over sine squared x. Then I'm going to pull out common the negative 1, so I get sine squared x plus cos squared x over sine squared x. And that will give me, well, sine squared x plus cos squared x is 1, so it's negative 1 over sine squared x, which of course is what we want, which is negative cosec squared x. Okay, now once you know your trig differentiations, again you only need to remember sine and cos, then you can differentiate any trig function. So I'm just going to have a quick look at a couple here. So we'll have a look at number 27. We've got y equals 2 cos of 3x. So it's quite important. So dy dx. Okay, so cos becomes negative sine, so it's minus 2 sine of 3x. Remember, the 3x is the angle, and then multiplied by the derivative of the inside. So again, this is your dou bit, and this is your diff. So you'd end up with negative 6 sine of 3x. And really important to remember, when you differentiate, the angle doesn't change. Okay, and we'll just have a look at number 28. So notice the trig function is tan, the angle is x plus pi over 4. So dy dx, differentiate tan, you get sec squared, so it's going to be sec squared of x plus pi over 4. And then if you differentiate the inside, you just get 1. Okay, so that doesn't make any difference. So therefore, dy dx is sec squared of x plus pi over 4. Okay, so you just need to practice